All right, welcome everybody to this week's Green Bank Observatory Community Zoom. A couple pieces of good news I'd like to share this week for the director's report. And the first is that Green Bank Observatory has been awarded an increment to its grant funding from the NSF of $5.3 million. And this money is going to be used to support the new track and grout for the Green Bank telescope. So after 20 years of hard work, the track and grout system on the base of the telescope is in some need of repair, and so the money will be used to purchase 48 new wear plates. Those are the plates that the telescope travels on, and then to replace some of the grout pockets, in fact, all of the grout pockets around the track that support those plates. So we are very grateful to the National Science Foundation for this increment. We will put the money to good use, and the intention is to ensure the smooth operation of the telescope for the next 20 years. So that's good news indeed. The second piece of news is the Jansky lecture. The Jansky lecture this year will be Francoise Combs, and one of those lectures will be at Green Bank Observatory. So I will post those links. February 15th, Francoise will be visiting Green Bank. And for those of you in the area, please feel free to stop by. And I'm pretty sure that will also be a Zoom link so that people can look in. So that's my news. I'll hand it off to Jay, who will introduce today's speaker.
Thanks very much, Jim. Today's speaker is Jack Orlowski-Scherer, who tells me that today he's from the University of Pennsylvania and tomorrow will be from McGill University. He'll be talking to us today on constraints on the thermodynamic state of X-ray bubbles in MS0735 with Mustang II. And let me remind everyone that there will be a time for questions and answers, and if you will submit your questions using the Q&A button on the lower right. Take it away, Jack.
Yep. Thanks so much for the introduction. So let me go to share. Oh, nope, share's there. And so everyone should be able to see my screen. Yeah.
Yes, we can see it.
Great. Okay, just double checking. Thanks for the introduction. So I'm Jack. I'm as of just finished up my graduate work at the University of Pennsylvania. I'm starting a postdoc at McGill tomorrow, working with John Sievers. Part of my research has focused on looking at using the SC effect to investigate clusters, and so as part of that, I led a project that analyzed some data Mustang II collected on the cluster MS0735. So let's start with a little introduction to feedback in clusters and why we actually care about looking at clusters in ASC. So there's a important problem that has developed over the last couple of years with clusters. So it's known that the radial cooling timescales for clusters are much shorter than their lifetime. The average cluster is several billions of years old, and the gas in those clusters should radiate away their heat in shorter timescales. So the centers of these clusters should have reservoirs of cool, dense gas, which should be driving star formation at a very high rate in the galaxies that live in these clusters of galaxies. But that is not observed. So a direct observation of the cores of clusters reveals a deficit of soft X-rays that would be associated with these reservoirs of cool gas, and then indirectly the observed star formation rates in these clusters are lower than expected if there were these big reservoirs of cooled dense gas at the cores of clusters. So you can see here, this plot on the right is essentially just showing what I said on the left, that for the age of the clusters, we expect basically all the gas out to a pretty far radius in the cluster to have cooled, but that not shown on this plot. That is not what we observed. So why is that happening? So there's probably a variety of mechanisms involved, but probably the dominant one is mechanical feedback and reheating of the ICM. ICM being the intracluster media. So the way this goes is that you have a active galactic nuclei at the center of the cluster, mass is accreting onto that AGN, and it forms jets of super accelerated particles, and those jets go out into the ICM and they interact with the ICM and they reheat the ICM. And so this counteracts the radiative cooling of the ICM, and so you end up not forming these as much, you don't have as cold and as much gas at the center of clusters because it's being reheated by these jets. So this is a VLA image of MS0735, which is the cluster that I'm talking about today. And so this is a 327 megahertz image. So these two antenna-like lines going off here and are jets that are coming off from the AGN. And you can see they're quite large. They're going out here to several hundred kiloparsecs. And it's known that these jets terminate in large X-ray cavities, which presumably are being sourced by the jets. What's not well understood is how exactly the jets are forming those cavities. So you could either have like a very simple direct mechanical picture where the jets are forming shocks and those shocks are supporting the bubbles, or there could be a more complicated, there could be something more complicated going on. You could imagine it's known that there are magnetic fields that are associated with these jets, and so the magnetic fields can be coupling to the plasma in the bubbles and providing pressure support that way. We really, as of right now, don't have any way of distinguishing between those two scenarios. So talking a little more about the bubbles, so they're called I call them X-ray bubbles in the title of my talk, even though this is an SC talk. The reason for that is that they're primarily observed in the X-ray. So this is again MS0735. This now is an X-ray image. You can see the cluster very clearly in the core, and then you can see up here in the top left, and then more faintly in the bottom right, a pair of bubbles that are notable because of the deficit of emission coming from them. This is a Chandra image. And so X-ray is nice because it's got a lot of resolution and sensitivity, and so you can see these bubbles pretty clearly. However, it's not, without additional sources of information, the X-ray data is not sensitive to the full thermodynamic state of the bubbles. You can measure the temperature, but you can't measure the pressure. And because of that, you can't distinguish between different support scenarios for these cavities. However, recently submillimeter experiments have reached a sufficient resolution and sensitivity that you can also detect these cavities in the SC effect. So this was first done by Zubair Abdullah, who used a karma array, which I'll talk about in a second. And as far as I know, we're the second to detect these cavities. And now the SC effect, of course, is sensitive to the integrated line of sight pressure. And so that allows you to, probe the pressure in the cavities. And so you can actually constrain the thermodynamic support, what the support mechanism for these cavities is. So talking a little bit more about MS0735 now specifically. So MS0735 is a relatively large cluster, most notable for containing possibly the most active known AGN, certainly one of the most active known AGN that sources these huge X-ray, it has a very, very energetic jet, and that jet is sourcing these huge radio bubbles. So what you're seeing on the right here is an SZ image of MS0735, which was made using the karma instrument and laid out in the paper led by Zubair Abdullah that I've linked there. The white overlaid contours here are the VLA images that I showed a couple slides ago. So these are the jets, and the contours in black are SE contours, while the red circles show the X-ray identified bubble locations. The crosses are the pointings for the karma array. They aren't actually the bubble center locations. That can be a little confusing. And so you can see that there's good agreement here between all three probes of the cluster. We have the red circle lines aligns pretty well with the black contours and also overlays nicely with the jets. So Zubair made just about a 5 sigma detection of these bubbles. And so was able to constrain them to be very highly suppressed, meaning that there was very little emission. There's very little SE emission, quote unquote emission, coming from within the bubbles, which is consistent with either very, very hot plasma in the range of hundreds of keV, or with some sort of non-thermal pressure support. However, due to the relatively low detection, I'm not going to call 5 low, but like relatively low detection significance, the error bars on that are quite large, about 30 or 35%. And so essentially what we set out to do is just to improve upon these constraints using Mustang II. So everyone here is familiar with the GBT, so I won't get into that. If you're not quite familiar with Mustang II, it's a high sensitivity 90 gigahertz instrument that's on the GBT. It has a relatively, it has a field of view of about 4 and a bit arc seconds, which means that it can instantaneously view all or most of a cluster, but it also has a resolution that you need to see these bubbles. For reference, these are just about it. They're a little less than an arc minute across. So yeah, so the Mustang team applied before and got time to observe MS0735. And then I led the analysis work to essentially model those bubbles on the data. So what you're seeing on the right here is the Mustang II image of MS0735. You can see the central AGN here. I've overlaid the green circles are the same as the red circles in Zubair's paper. They're showing you where the X-ray bubbles are. We've got contours here, and dashed are, this is all in signal to noise. These dashed lines are, I believe, half SN, and the solid lines are 1 signal noise. And so you can see these bubbles really clearly now, especially this top one just pops out even by eye. Top left one pops out by eye. It's a little hard to know exactly how much better we are than Karma. Karma is an interferometric array, so its sensitivity numbers are a little weird, but it's something like 2 to 3 times of an improvement with Mustang II. And of course, that translates into a better ability to distinguish between methods of support. As part of this project, we developed an extension to the Mustang II pipeline that allows us to fit more complicated models like this one to the data in a pretty high efficiency way. So we fit this to a double ISO beta model. As many parameters as we could, we constrained to the X-ray measured values. The X-ray is still a lot more sensitive. So for things like the geometry of the cluster, it sets much more precise constraints than we can get. And then fit for the the amplitudes of the cluster profiles, as well as the amplitude of the suppression within the bubble. And before I show the residuals, I have this really nice plot that Luca Di Mascola made. So that's the Mustang observation, and that's the Chandra, and you can see this really just excellent agreement between the locations of the bubbles in the X-ray and the SC. It's really, it's good to look at. So these are the residuals. This is the residual subtraction of our model. We make about a 6.5 sigma detection of the bubbles, where that's made with reference to the model without the bubbles. And the way we actually quantify this is by what we call the suppression factor, which is just all we do is within the bubble, we reduce the SC emission by a factor F that we call the suppression factor. So if F is 1, then there's no SC emission whatsoever from the bubble, and if F is 0, then you have whatever SC emission you would expect just from the beta profiles without, as if they were emitting normally. So the exact suppression factor we find depends on some of the modeling assumptions we make, but at the lowest, we find that it's about 0.33 plus or minus 0.7, and I'll translate that into something usable on the next slide. We also detect, we also included in this model, cocoon shock that was originally reported in the Chandra observations of MS0735, and we make a detection of that cocoon shock at more than about 10 sigma. So how do you actually turn this into an actual constraint on the thermodynamic state? So you can turn the suppression factor in a thermal support scenario. The amount of suppression you see can be directly related to the temperature of the plasma, and so that's what we do here. So the blue curve here shows the lowest suppression factor that we found based on our modeling choices, and the orange shows the highest. The bands here indicate 1 sigma uncertainty. So a couple things I want to point out. The first thing I want to point out is that the spread due to modeling choices is much bigger at this point than the statistical uncertainty on these results. So one of the drivers here is, for example, the position of the bubbles along the line of sight. We have no constraint on that. The Chandra also doesn't provide a constraint on that. And so that, depending on where along the line of sight it is, the emission that you expect from it changes. And so the suppression factor that you infer from that also changes. This sort of effect can be broken if you have multi-Crowick observations of the cluster, for example, because the thermal non-thermal support cases also have a different spectral signature, and so while you still have this degeneracy with the line of sight, so the amplitude of the suppression, the spectral effect, you can distinguish the scenarios in this using the spectral information that you have. This lowest one here is consistent with a temperature of somewhere around like 70 keV, which is quite hot, but not necessarily physically hot, whereas this top one requires the plasma to be in the range of about 1000 keV. Yeah, so the takeaway here is that there's likely at least some non-thermal pressure support, but unfortunately without the ability to constrain our modeling choices, it's hard to say anything more than that. Even if you have more sensitivity, you would just shrink these error bars about their respective means, and you wouldn't actually reduce the discrepancy between the two. So quickly going through some conclusions. So in the purely thermal pressure support scenario, the support for cavities in MS0735 must be provided by a population of thermal electrons with temperature greater than 100 keV at 2.5 sigma. I realize that is slightly discrepant with what I just said. That's because the lower bound is for only one of the two bubbles. The other bubble requires at least 100 keV. So while one of the bubbles might have non-thermal pressure support, the other one requires thermal pressure support at least 100 keV. Alternatively, pressure support by non-thermal mechanisms is not ruled out by our data, although it's not required either. And finally, looking to the future, multi-frequency, high-resolution observations around the SC, in the SC, spectrum range could help break these modeling degeneracies and allow us to say much more definitively what the pressure support in these bubbles is. So slightly long, but not too long. So thank you all very much for listening, and we'll open to questions now.
Thanks very much, Jack, for an excellent presentation. Let me remind everyone that this is being recorded for future viewing on the Green Bank Observatory website. And if you have questions, please submit them through the Q&A button on the lower right of your screen.
Will I be able to see them, or will someone relay them to me?
I'll relay them to you.
Okay, great, thank you.
That's probably the safest way as they come in. And people are typing furiously, I'm sure.
We actually do have a hand raised from the attendees group.
Oh, thank you. Let me see. How do we get to that person?
This is a question. I don't know if it's a question or a comment from Daniel Wang. Daniel, if you have a question, please put it in the Q&A.
Yeah. Meanwhile, we do have a question. How about rotation measure maps of cavities?
Sorry, what do you mean by that? Like, what about them?
That's the extent of the question. Do you have rotation measure maps of the cavities, I guess is the question.
No, we don't.
Okay.
We do not.
All right. And here comes some more. Could you elaborate why the thermal suppression depends on the SZE?
Why the thermal suppression? Well, it's more the other way around, right? Like if you have very hot, if you have it in a thermal, like the SC effect, right, is ultimately sourced by the momentum distribution of the electrons in the ICM. So if you change the momentum distribution, then you're going to change the effect of the SC, the SC effect, right? So like when you the simplest thing you can do is you can change the temperature, and that sort of changes the scaling of the SC effect. And so that's what we're sensitive to. But if you had a multi-chroic instrument, if you have a non-thermal effect, right, it's going to create its own completely different non-thermal SC effect. And so that'll look different spectrally than the thermal effect will.
Okay, we have a question. What's the temperature difference between the cavity and the surrounding ICM?
That is a good question. We think they're probably in equilibrium, but we're not sure.
Okay.
We don't, just to be clear, we don't have constraints on the temperature. Those are sourced by Chandra.
Okay. We had a question about, are there any links for further viewing of this? And I'm not quite sure what that refers to.
Well, our paper's up on archive. I linked to it at the front of my talk.
Okay.
I don't know if you guys linked the, I don't know if you guys linked the talk somewhere, but yeah.
Yeah, we do. It'll be on the Green Bank Observatory website later today. And here's a question. Dependence of the SCE on temperature is what I meant to ask, as you seem to indicate. I thought that only non-thermal pressure affects the suppression.
No, at a given frequency, if you change the temperature, then you essentially change like the scattering cross section. And so that changes the SC effect.
All right. Is there any polarization of the residual signal?
Mustang II is not polarization sensitive. I would love to be able to answer that question with a polarization sensitive instrument, but we don't have one, so we can't. Would be good to know, but we don't.
Would you expect it?
Maybe. Maybe. I mean, you could imagine if there were like a magnetic coupling, that there might be some sort of polarization of, there might be, like if you have a magnetic field which is polarizing the ICM, that could lead to a polarization in the residual SC signal. But I don't know how strong that effect is, so I can't say whether that could be a like 10 to the -10 effect, and like you'd never see it. So yeah. I don't know how strong it is.
Okay, let's wait another minute and see if there are any other questions coming in. We have a few more minutes. Well, if not, thanks again very much, Jack, for an excellent presentation.
My pleasure.
And-
Thanks for having me.
Let me remind everyone that the next presentation, 2 weeks from now, September 14th, we go from galaxy clusters to local pieces of rock. Lance Benner talking on the Apophis Planetary Defense Campaign. Thanks and hope to see you all then. Goodbye.